In this lecture, we consider the algebraic geometric codes, which are derived from the elliptic, hyperelliptic, and what are called Hermitian function fields. And for this, it's going to be kind of survey talk, survey lecture, and mainly we follow the paper which is published by Ian Black and et al. In IEEE, and the references therein. The first case, I want to consider the elliptic function fields. Let me briefly recall the definition. They are genus 1, and they have there exists a rational point, and in general we denote this point as a base point or the O infinity or the place at infinity. And thanks to this definition, indeed we can explicitly write their equations regarding the algebraic relation of x and y. And here f of x denote degree 3 square-free polynomial in the polynomial ring K of x. And so that means in order to construct an algebraic geometric code, we need to consider its rational points. And like in the Ritz-Solomon case, let me also consider the place at infinity, so the base point O. Because it is going to be a candidate to produce a divisor G. And in other words, by using these n rational points, we can introduce a divisor D, and with this base point, let me consider the divisor G, which has m times O for some positive integer m. And by theorem 2.2.2, we know that indeed we can produce a linear code by considering the evaluations of the functions in the Riemann-Roch space L of G at this given distinct places. And we know the parameters if the degree of if m is strictly less than n. We know this is going to be, this evaluation map is going to be injective, and the linear code is going to have dimension m, and its minimum distance will be bounded below n minus m. And in elliptic function field, the dimension can be also n plus 1, so this is going to be also the case. I will refer to later. But one of the facts about the algebraic geometric codes, which are derived from the elliptic function fields, almost all these codes have parameters n, m, and n minus d. So that means they are falling short of the singleton bound by 1. And there are also some exceptions. And one of the exceptional case it is given by Van der Veer, if I'm not pronouncing wrongly. This example also credited to by Ruth Pelikan. And indeed, they gave an example of a linear code which is of length 6, dimension 3, and the minimum distance 4 over the finite field F4, obtained from the elliptic function field or the elliptic curve, and indeed this is an MPS. So it doesn't satisfy these parameters. And okay, in general, if you want to understand evaluation codes from the algebraic from elliptic function fields, the thing we can check is there are some, actually we need to clarify some situations, like if, for instance, if we want to produce a generator matrix, we want to write the explicit basis of the Riemann-Roch space of L of G, or obviously the length of the algebraic geometry is closely related to the number of the rational points. And first, let me try to explain what can be the dimension, or is it possible to write the basis of a Riemann-Roch space of L of G when G is of the form M times O. And indeed, for the base point O, we know that the functions x and y has poles at the base point O. Indeed, this is going to be O of order 2 and 3 respectively. And by using this fact, indeed, we also consider the Riemann-Roch spaces of 2O, O, 3O, and we can easily check that these functions belong to the Riemann-Roch space of 2 and 3O. And by the Riemann-Roch theorem, indeed, we can verify that they are going to have dimension 2 and 3, and these given functions forms the basis. And in general, for given base point or the point at infinity or the place of infinity, the general form of the basis was given by Riencourt and Michon. And indeed, they show that the Riemann-Roch space of M times O, the divisor MO, has a basis in this form from 1x to the delta y x to the delta hat. And here delta denote the largest integer, which is less than or equal to m over 2, and delta hat denotes the floor function m minus 2 over 2. And thanks to this explicit form, we can conclude that it is dimension delta plus 2. And in the case of m is strictly less than n, by the lecture notes or by corollary 2 to 3 from Stitte note, we can conclude that the algebraic geometric code, which is produced by the evaluations of the functions of the Riemann-Roch spaces MO, is dimension delta hat plus 2, or it is going to be m plus 1 if m is even, and it's going to be M when M is odd. And this gives us the information about the dimension of an algebraic geometric cos from elliptic function fields. And for the length, as I mentioned before, we need to consider the number of the rational places of a function field over a finite field fq of genus G. And let me denote this number of rational places function field with the constant field fq of genus G by n of f. And indeed, this is a quite difficult question. I mean, to compute the number of the rational places of a function fields or of an algebraic curve, because as the genus grows, the number of the places increases. But at least we have an estimation, and which is indeed a famous theorem. Which is called the Husserl bound. It gives us the estimation of the rational places of a function field f, and it basically says that the number of the rational places is going to be what's called the Husserl interval, and here G denotes the genus of the function field, and Q denotes the size of the constant field fq. And in certain cases, in the elliptic function field case, we know that the maximum number of the rational points can be at most 2 square root plus q plus 1, 2 square root of q plus 1. And indeed, to be able to construct a linear cos of a long length, we need to consider the maximal cases. Indeed, we want to compute the number of the rational places exactly. And in order to give some information about the number of rational places of an elliptic curve, here I just want to present some results from the Silverman by the arithmetic of the elliptic curves. So indeed, we treat them elliptic curves as an elliptic function fields. And just for this case, let me denote the number of rational places or the rational points by the size of this abelian group. And here E is defined like in the elliptic function field as y squared is equal to f of x with degree 3 scale-free polynomial. And indeed, if we want to compute, I mean, if here Q denotes the prime power, and if we want to compute the number of the rational places, it's going to be sufficient to know enough information about the number of the rational places over FP. Indeed, I mean, more explicitly, or in general context, if we consider the theorem in chapter 5, theorem 2.3.1 from the Silverman, which says that if we have an elliptic curve or the elliptic function field over the extension field fq to the k, they introduce, so let me also recall Hasse-Weil bound again. So they introduce this quantity, which is unique. But here we consider the Q. I mean, if you want to compute the number of the rational places over FQ to the K, we introduce what is called the trace of the Frobenius. Indeed, here by the Frobenius map, by the Frobenius, we mean the Frobenius map. So like in the finite field, which maps to coordinates of x, y, the q powers of them. And indeed, it forms a linear map, and by the trace, we consider the trace of this linear map. And depending on this quantity, the number of the rational places or the rational points over FQ to the K can be computed as Q to the K plus 1 minus alpha to the K and beta to the K. Here alpha and beta are roots x square minus tx plus 1 minus q. So if we know the number of the rational places over the base field, we can exactly compute the number of the rational places over the extension field. And if particularly Q is written as P to the E, here P denotes the characteristic of FQ. In this case, the number of the rational places is computed as Q plus 1 plus the largest integer, which is less than or equal to 2 times square root of Q, if P does not divide this quantity. And if the power E is odd, it is computed as Q plus floor function of 2 times square root of Q. So, and this shows us the number of the possible rational places we may consider for a given elliptic function field or the elliptic curves. So what I recommend in general for this, the examples we will consider in this lecture, to play with some toy examples which are supported by SageMath and Magma, and to understand what are the number of the rational places and what can be the maximal option, particularly regarding the Hasse-Weil bound. And similarly, if we want to consider the evaluation map, it can be nice to understand what kind of generator matrices can we have for an algebraic geometric code, which is produced by elliptic function fields.